No, I think really next time we just can try with Sravan or maybe with you, Luca. I will show you what to do because it requires some 5 simple steps, but they have to be done.
Yeah.
Preferably the correct order.
Okay.
Because you see, the problem is that I have to enter Google, and you can imagine it's not a trivial thing for me.
At 5 factorial, it is not a small number because you need to make 5 steps in different orders. So the number of possibility is too big, I would say.
Yes.
You cannot do it in a few minutes.
Yes, it requires some accuracy. You're right.
Coming, I guess. Okay. But the speaker, she is not yet here.
No, she will come 5 minutes before.
Just a moment.
Yes, so I have to make someone co-host, yes?
Yeah. No, the speaker will come just 5 minutes before. She will come soon.
Just what?
She told me she will join 5 minutes before 5.
So
you should arrive soon.
Okay, yes. We'll be back in a moment.
Flaminia is here. Hello, Flaminia.
Hey, sorry, I was.
No problem. How are you?
Hello.
How are you?
Oh, very nice place. Where are you? Is it your
At
place?
home.
Oh,
Yeah.
Very nice. Okay. Yeah, now maybe we can try the slide sharing.
Yes.
Wait a second. Now you can.
Can you see?
Oh, yes.
Okay. And now I can try to. So now you should see only the slides, right?
Yeah, we also see the pointer, so it's fine.
This one, the red one.
The red one and also the how do you call it? Also that one.
Also the arrow. You see also the arrow. Okay.
Yeah, also the arrow.
Okay.
But I forgot to ask you, Flaminia. Usually we live stream the talk on YouTube. Is it okay for you?
Yeah.
Okay. Okay, so I think we still have 5 minutes.
Yes.
We can just wait. And also, do you prefer questions during the talk or at the end?
No,
Audience?
if there are questions during the talk, this is fine with me.
Oh, hello, Flaminia. Here is Arina. Yes.
Sorry?
I'm here because I will open the conference in few minutes. We still have, I have to check, maybe 2 or 3 minutes.
Yeah.
5, actually. It's okay.
It's okay. Because I'm in some recreation center now. They just came here to measure my pressure.
Luca, and you are now in Italy?
Yeah, I'm still in Italy. I'm going back to Stockholm next week. End of next
Maybe
week.
I'll turn on the lights. I don't know. It'll be like in 1 hour.
Are you in Switzerland now, Flaminia?
Yeah, I'm in Zurich.
Okay.
Yeah.
Good for you. You can ski almost every day.
Actually, today it's pretty warm. It was unexpected. It was cold in the past days, but today.
Yeah, but I mean, still.
Yeah,
it's not far from you.
Yeah. No, actually, from the bus, I could see the mountains with snow on top.
Good.
And the temperature is minus? or plus?
No, it's today it's actually quite mild. I think it's above 10 degrees.
Oh, okay, then
Oh,
it's
I see.
quite warm.
Yeah, yeah.
So it's spring.
Yeah, it's spring. Today it really felt like spring.
Good.
Here we have a winter because we have a lot of snow whole day.
Where are you based?
I'm in Moscow now.
Ah, okay. So yeah, it's cold.
In fact, near to Moscow, yes.
I also sit in Shanghai and have plus 26, but it's okay.
26?
Yeah.
Oh,
No, I mean, not now. Now it's midnight, but it's okay.
Wow.
Mhm.
take my. Want to check. We still take 2 minutes.
Yeah, it's still okay, sometime.
By the way, Luca, do you remember when there will be time shift in Europe?
Now it's a time to start, but maybe we can't wait 1 minute.
Yeah.
Because typically I see that people
Hey,
still
Alex, let me
coming,
check.
as usual.
Mm.
Hello, LinkedIn. Long time no see. She's in Zurich with me. So we saw each other just 1 hour ago, 2 hours ago.
Nice.
You're muted.
Yeah, muted, yeah.
I see you are moving to a different place now, Flaminia, from the background.
Yeah, the office was busy, so I couldn't give the talk from the office.
Alex, but there will be 26th of March.
Oh, okay, so we'll have a couple of extra seminars without any hassle.
They will
That's good.
change to summertime.
Yeah, I wait for it because then it will be not midnight, it will be 23 o'clock.
Because it doesn't change in your case. It doesn't.
Yes, yes.
Okay, maybe we can start. Hello, everybody. Today we have a pleasure to have a talk by Flaminia Giacomini. She will tell us about quantum reference frames, the relation perspective on non-classical space-time. Okay, please, 1 hour.
Thank you very much for the introduction, and thank you very much for this nice invitation. I'm very happy to be able to present my research here. And so today, this is an overview talk, and I will focus on quantum reference frames, which is a way to associate a reference frame to a quantum system. So for instance, to jump to the perspective, loosely speaking, of a quantum system that in a quantum superposition of two positions. And I would like to argue, and this is really more like an argument, it's not a result that we have achieved so far, but so it's a research program that is really at the start, that this can be helpful to talk about non-classical space-time. And I would And I will motivate that by giving you two examples at the interface between quantum reference frames and gravity. But before, let me just first introduce the general scope of this research. So in our two main pillars of physics, general relativity and quantum theory, they both rest on spacetime, which is a classical notion. However, at the interface between gravity and quantum theory, we expect that this notion will no longer be valid and that it will have to be replaced by a more general one that currently we do not know what it is. And there has been a lot of work on that in quantum gravity. And typically, this work focuses in the high energy regime, so talking about Planck scale physics. This is not the approach that I will take in this talk. I will instead focus on a different approach that is in the low energies, where gravity is treated perturbatively, and we can meaningfully talk about quantum particles. And in particular, the research that focuses on this approach asks some fundamental questions about the nature of time, space, causality, reference frames. And this is not the full quantum gravity regime, but it has the strength that it provides us with concrete scenarios with an immediate physical meaning. And to understand that, let me just give you an example of how we deal with this situation, both mathematically and which type of situations, of physical situation, it gives rise to. To do that, let us consider Einstein's equations, so general relativity. And well, I don't have to explain that here to this audience, but just to set the stage, they connect the metric to the matter. And a feature of this of general relativity is that we can only write these equations with classical matter. However, from quantum theory, we know that matter is fundamentally quantum. As far as we know, the best description that we have of matter is quantum. And so if it is natural to think, well, what happens if we want to plug a quantum stress energy tensor here on the right-hand side of Einstein's equations? And in general, we do not know what happens. We cannot solve this equation here, and we do not have a fully quantum version of this equation here. So there are many possible approaches to answer this, but the one that I would like to focus on is to restrict to a simpler scenario, namely the scenario in which you linearize the left-hand side of this equation, and then you consider gravity as a quantum, so as a background spacetime that is typically taken as Minkowski plus a quantum perturbation. And which type, so in this case, the mathematical framework is clear. So we can solve these equations. And it gives rise to scenarios that I want to argue that they are interesting to talk about. And for instance, this can describe a massive quantum particle that is in a quantum superposition of two positions, as what I depicted here. Now, one can think, okay, in this case, I have a background spacetime. I can always refer to my background spacetime, and then I can do all my calculations by relying on that. So why am I saying that this is not a classical spacetime? And the reason is that it is fundamentally not a classical spacetime, because I have a quantum source of a gravitational field. So I am beyond the solution, the classical solution of Einstein's equations. And in addition, I could even measure that. Of course, we don't have the precision now to get to this scale. But for instance, if I put a quantum clock here, the quantum clock will feel a difference whether the mass is localized here or here. So it is measurable. And it's true that we do not have this precision, but experiments are trying to get there. And so what is the status, the experimental status now? There are two main directions that experiments are following. And on the left-hand side, there is the direction in which they try to measure the gravitational properties of smaller and smaller objects, lighter and lighter objects. And now, to the best of my knowledge, this is still the state of the art. So Markus Aspelmayer group in Vienna measured the gravitational coupling, so the gravitational interaction between two spheres that weigh as little as 90 milligrams. And so the idea here is now to decrease even more the masses of which we can measure the gravitational field. On the other side, here on the right, there is the opposite goal, which is to measure the quantum properties of more and more macroscopic objects. And there is more than one way of doing that. So for instance, here they try to increase the mass. This is a quantum interference of molecules. And this is the mass that they achieved so far. And instead here, we have an experiment that is an atom interferometer, which instead managed to achieve a quantum superposition at the level of atoms. So these are smaller masses, but of half a meter. So an atom that is put at a half a meter superposition distance. So in the end, the goal would be to bridge these two regimes and to measure the gravitational field that is sourced by a quantum object, by a mass that is in a quantum superposition. And this is, of course, very hard. So it's not something that will be done tomorrow, maybe in 10, 20 years. And mainly it is limited by decoherence and scattering. And in this paper by Markus Aspelmayer from last year, you have a very good review of what the state of the art is for these experiments. Now, as I mentioned, this is clearly not the full quantum gravity regime. So why is this interesting? Why can it contribute towards answering questions that are relevant also to quantum gravity? And here I would like to list three motivations that are my personal reasons why I think this is interesting. So if you ask somebody else, they will have some other reason. And I list them from the most conservative to the most ambitious one. So the first motivation that I can find is that to date, we do not know which observation would prove in a compelling way that gravity has quantum features. All the experiments that we have so far are perfectly consistent with the classical gravitational field. So we will have experimental guidance, as I showed you in the previous slide. And so it is really important that theorists now understand exactly and very precisely what one can say by performing these experiments. So the second motivation that I want to list is that there are many conceptual questions in quantum gravity that already show up in this regime. And for instance, so as I argued, classical spacetime, but also quantum time, and this can be studied by using quantum clocks, causality, what happens to causality at the interface between quantum theory and gravity, or what are the relevant observables, or how do I partition the full Hilbert space into local algebras or subsystems? These are all questions that already appear in this regime. And so shedding light on these questions when one has concrete physical systems and concrete scenarios then can be helpful. And finally, the most ambitious motivation is that, in this research, one typically imports quantum information tools to answer questions at the interface between quantum theory and gravity. So for instance, quantum information theorems and protocols. And a fundamental feature of quantum information is that it is not tied to a specific regime, but it is tied to the probabilistic description of the theory and to the first principles of the theory. So the hope is that by doing this type of study, one can identify the fundamental principles that underlie the theory. And this maybe can also point us towards generalizing the theory at higher energies. So Now we can get into the detail of the main topic of the talk, which is quantum reference frames. But before I introduce you to the notion of quantum reference frames, and as a disclaimer, I will just talk about a specific approach to quantum reference frames, but quantum reference frames have been around in quantum gravity and quantum information since 1967, in both, same year for both fields. Then let me just set the stage and also as a terminology and tell you what I mean and when I talk about a reference frame. So in physics, when we talk about reference frames, we typically talk about a set of axes and the state of motion. And this is very helpful because it allows us to fix the point of view from which observations are carried out. And a very important feature, very important principle that we have in physics is that it doesn't matter which reference frame we pick, because in the end, they're all equally valid descriptions of physics. Now, let us focus in standard quantum mechanics, not relativistic, just with Galilean symmetry, so the simplest situation that we can consider. And let us imagine what happens when I want to do a reference frame transformation. In quantum mechanics, we encode reference frame transformations in unitary operations. So for instance, we can have a translation or a Galilean boost. And what I would like you to focus your attention on is this x0 and v. So these two are respectively the relative position between the initial and final reference frame and the relative velocity between the initial and final reference frame. And they enter the transformation as a parameter. So they're not operators, they're not dynamical quantities, they're just a parameter. And now we know that physical systems evolve, and in quantum mechanics, they evolve according to the Schrödinger equation. When I change the quantum reference frame, I have that, when I change the reference frame, I have that the Schrödinger equation is mapped into another Schrödinger equation, provided that the Hamiltonian changes according to this law, where U is the reference frame transformation. And so this expresses the covariance of physical laws. In addition, we say that a reference frame transformation is a symmetry of the dynamics if the functional form of the Hamiltonian after the transformation is the same as the functional form of the Hamiltonian before the transformation. Okay. So now, let us take, again, a very simple situation where we have three parties. We have A, B, and C. And we want to describe them. For instance, we want to take the perspective of C. Now, one of the features of the approach that I'm going to introduce about quantum reference frames is that it is relational. And it is relational for reasons that are related to the fact that general relativity is relational. So we wanted to have the same feature here. And so this means that basically the center of mass doesn't matter. It's not a physical degree of freedom. And the only meaningful degrees of freedom are the relational ones. So if I center my reference frame here in C, the only relevant degrees of freedom are the distance between A and C and the distance between B and C. But if I instead center my reference frame in A, then the relevant degrees of freedom are the relative position between C and A and the relative position between B and A. So the amount of information is the same, it's just reshuffled between the subsystems. But now, if we think about it from an operational perspective, we know that whenever we take an observation, we make a measurement, we use physical systems, and we always take as reference a physical object. So for instance, if I want to measure the distance between two objects, then I will take a meter and I will put one end of the meter on say, the edge of this table, and then I will take it until the object that I want to measure, and I will count how many ticks are in the meter. So what this is to say that reference frames are physical systems, and physical systems are ultimately quantum systems. So now then a natural question that we can ask is, does it make sense to associate a quantum reference frame at this point to an object, to the position of an object that is in a quantum superposition? So in other words, does it make sense to consider reference frames which are in a quantum relation relative to each other? So they can be in a superposition or even entangled relative to each other. And if I'm asking this question and I'm talking about quantum reference frames, you already know that the answer is yes, at least in a certain sense. But let me specify in which sense. So we want to find a quantum reference frame transformation that takes us from a situation in which we center our quantum reference frame on one particle, and then we describe A and B in a quantum state, to a situation in which we center the quantum reference frame on this particle that is in a quantum superposition, and then at this point becomes the center of the reference frame. So it's as if we want to localize this particle. But at this point, this particle will describe B and C in a quantum state. So the simplest example that one can think of is, imagine that I have a quantum system that is in a quantum superposition of being here and there. And then I go to the perspective of this quantum system. So this quantum system sees me as delocalized. So that's roughly the idea. Now, let us take the simplest transformation just to see a specific case. And this is a special translation in one dimension. Now, we have initially that the reference frame is centered in C. And then we describe the state of A and B as A is localized and B is actually can be any state. But just for simplicity, I drew it in a fixed position. So now, the reasoning that I'm using here is that I first do the transformation in a case in which the standard reference frame transformation holds, and then I will generalize it to a quantum reference frame. So now we want to shift the origin of our reference frame to the particle A. And here it's clear what I have to do because I have just one position. So I will just apply a translation operator. And then what I will obtain is that A is at the origin, and then B is translated by an amount x1. But also, since I'm in a relational formulation, I also have to describe my previous reference frame from the perspective of the new reference frame. And so this will be in minus x1, and I will assign it a label C. So this transformation can be written formally in this way, where this is just a translation operator in quantum mechanics. And this one here is called the parity swap operator. And it does exactly what I told you from here to here. So it sends x to minus x and swaps the label A with C. So this is in order to complete the transformation and also describe the old reference frame from the perspective of the new one. Now, let us consider a slightly more complicated situation. So our quantum reference frame A now is in a quantum superposition of two positions. So x1 plus x2. In this case, we cannot apply a standard translation anymore because we don't have a single position by which to translate. So how do I do? A possibility is that I take seriously the linearity of quantum mechanics. And I say, okay, it's true, I don't have just a single position, but I can coherently translate by the amount, by the position of the reference frame. So I will just translate by every single position that the quantum reference frame has. In quantum information language, this is called a quantum control translation, where the control is the quantum reference frame of A, is the state of the quantum reference frame of A. So this means that what will happen is that when A is in X1, it will see B in X0 minus X1 here, and C in minus X1. But when A was in X2, then B will be in X0 minus X2, and C will be in minus X2. And since this translation is done coherently, then I am mapping this state that is a product state into an entangled state. And this is actually a very general feature of quantum reference frame transformations, that entanglement and superposition are not defined a priori, but they depend on our choice of the quantum reference frame. And if you look at this transformation in this case, so this is very similar to what I had on the previous slide, but it has one crucial difference. That is that the parameter of the transformation, remember from the first slide when I introduced the reference frame transformations, is not a parameter anymore, but it is an operator that acts on an additional Hilbert space that I didn't have in the previous slide, and that is the Hilbert space of the quantum reference frame. So the recipe that I'm giving you now is that if I want to promote a reference frame transformation to a quantum reference frame transformation, I should just take the standard reference frame transformation and promote the parameter to an operator. So that's roughly the recipe that we have. Then it's more complicated than that, but on the first approximation, that's what happens. And in addition, this transformation is unitary. So I can just go from here to here or from here to here. So these two descriptions are equivalent. Now, consequences. I've already mentioned that entanglement and superposition are quantum reference frame dependent. But then here I also gave you the simplest transformation, but we have actually many more that we can consider. And in particular, it's interesting to consider a set that I will tell you in the next slide of some extended Galilean transformations that we will talk about. But so far, all the transformations that we have found have roughly this structure. For some of them, it's exact. For some of them, it's approximate. But roughly, what we find is that the quantum reference frame transformation is here a unitary that depends on this parameter, and this parameter specifies the type of transformation that I'm doing. So it can be special translation, Galilean boost, transformation to an accelerated reference frame, and so on. But then this parameter is not actually a parameter, but it is controlled on the state of the quantum reference frame. And this can be position, velocity, or some effective acceleration. And this is the case. So the accelerated case is the one that is not exact, but it is more complicated than what I'm telling you now, but it works roughly in this way. Now, so far, I have considered everything as frozen. I have not included any dynamics, but of course, we have a quantum system. We would like it to evolve. We would like to evolve it according to some Schrödinger equation and to some Hamiltonian. So let us imagine now that we have an initial Hamiltonian, and now we want to perform a reference frame transformation. Let's start with just a simple reference frame transformation that has, say, this form here. And this is the form of an extended Galilean transformation that was introduced by Daniel Greenberger. So now the Schrödinger equation, as I told you in the first slide, changes, the Hamiltonian in the Schrödinger equation changes according to this law. And so in particular, if I specify this quantity here to be either a translation or a Galilean boost, then a free particle Hamiltonian on some system B is mapped through this equation here to a free particle Hamiltonian of the system. How does that change when I consider quantum reference frames? Basically, it doesn't change, but there is an important caveat. So first, you remember the recipe that I gave you. We take these parameters of the transformation and we promote them on operators on the Hilbert space of the quantum reference frame. So the position operator for the translation, MPA divided by MA for the boost. And now we also have this additional Hilbert space. So we also want to give dynamical, the dynamics to the quantum reference frame itself. So we give a free particle Hamiltonian, for instance, to A, in addition to the particle that we had. So that's the thing that is more general, that we had to add the Hilbert space of the quantum reference frame and its Hamiltonian. But now, if it is possible to find some quantum reference frame transformations that correspond to the superposition of translations and superposition of Galilean boosts, such that this free particle Hamiltonian is mapped again into a free particle Hamiltonian, but where all labels A are now labels C. And this is the sense in which we talk about an extended symmetry of the dynamics for quantum reference frames. Okay, so this concludes this part, but then I promised at the beginning of the talk that I would give you a motivation of why this approach, so far I had no gravity at all, why it can be, why I hope that it can be helpful for gravity. And as I said, this is a research that is just starting now, so there's still, most of the work is yet to be done. So I'm just going to give you two examples that I think are promising towards this direction, but of course this still has to be explored and the main results still have to be obtained. So the first example that I want to give you is a possibility of generalizing the Einstein equivalence principle to quantum reference frames. And this can be done in two ways. One is more conservative, the other one is more speculative. So the first way that is more conservative is I am in a classical gravitational field, for instance, the gravitational field of the Earth, and I put a particle in a quantum superposition, for instance, in an atom interferometer. Now, we know that the value of the gravitational field at this point along this trajectory or along this trajectory is different because it's in a different potential. But we can find a quantum reference frame transformation to the quantum reference frame of this particle such that the metric is made locally Minkowskian at the origin of the quantum reference frame. In a more speculative way, we can instead consider a superposition of gravitational fields, where by superposition of gravitational fields, I mean two configurations that are roughly each of them corresponds to a classical gravitational field, but that is macroscopically distinguishable. And then we can consider a particle that is entangled with this superposition of gravitational fields. And even in this case, we can find a quantum reference frame transformation to the quantum reference frame centered on this particle that is such that the metric is locally Minkowskian at the origin of the quantum reference frame. So the implications of these two scenarios that I described are, well, first, for this case here, one can devise a test of this generalized Einstein equivalence principle for quantum reference frames by using entangled quantum clocks in an interferometric setup. And with a master's student, Carlos Cepollaro, we found that if this generalization of the Einstein equivalence principle is not valid, it doesn't even make sense to define the time evolution in the quantum in terms of the parameter of these clocks, of the time parameter that the clocks in the interferometer tell us. So we can actually make a model and bound the violations of this Einstein equivalence principle for quantum reference frames. In this other scenario, instead, we related it to Penrose state reduction. So Roger Penrose, when he argued for the spontaneous localization, he uses different arguments, but one of them is that there are these two fundamental principles of general relativity and quantum theory, the Einstein equivalence principle and this linear superposition principle, that are in conflict with one another. And so this conflict is resolved if one abandons one of them. And he wanted to put general relativity first, so he abandoned the principle of linear superposition. And hence there is the idea that if I put a massive body in a quantum superposition, then this is an unstable state, and one of the two amplitudes will die out after some time. But what we are proposing here is that it is not necessary to give up one of them. You can keep both of them if you're ready to generalize the Einstein equivalence principle also to this type of configurations. Now, let me switch to a more concrete approach that is instead, so I'm going back to this example of a mass in a quantum superposition. And in particular, so this is definitely not a new topic. This is something that has been discussed at least since 1957, when Richard Feynman at the Chapel Hill Conference proposed a thought experiment that involved a mass in a quantum superposition and concluded that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. And what Feynman meant by gravitational quantization is very precise. He meant that the state of the gravitational field is in a quantum superposition. Since then, there was a lot of literature on this topic, with many people arguing in favor of the quantization of the gravitational field, some people instead arguing that it should be kept classical. I don't have time to go through this literature, but just let me mention that this field was recently revived by these two experiments that came up, thought experiments that came up on the same day on the archive, which used a quantum information protocol. So it's basically a slight variation of Feynman's original thought experiment, but it involves two particles that become entangled by their gravitational interaction. And there is a lot of debate currently on what this thought experiment can tell us on the nature of the gravitational field. There are many different positions, and I don't want to go into the details of this debate, but basically there is no conclusion. So we do not know yet how far we can go with this experiment, if this experiment was actually performed, in assessing the nature of the gravitational field. So this is an open question. And so the basic situation is always putting a massive body in a quantum superposition. And now I want to add one additional question to the already existing ones, which is the superposition of gravitational fields a relative concept? So we have seen in quantum reference frames that entanglement and superposition are quantum reference frame dependent. And now I want to ask, can this be the case also for the gravitational field, and how general it is? And if this is true, what does this imply for these experiments that put a mass in a quantum superposition? And I do not have an answer for that. I only have one specific case in which we can look at. That is an experiment that was performed with atom interferometry techniques in a gravitational field. So let me tell you what this experiment is first. So this, it's called the gravitational Aharonov-Bohm experiment, and it was done last year in the group of Markasevich at Stanford. So this is an atomic fountain. What does this mean? You have to imagine this big cylinder that is 10 meters high, and there is a source on the bottom of the cylinder that shoots atoms up in the air. And then these atoms, just focus on the red atom in this figure, the blue one it's not important for the analysis that will follow. So these atoms, so this is the same red atom in a quantum superposition. And as you can see, the distance between these two arms of the interferometer is 25 centimeters. So by the way, this is the same group that did the half-a meter superposition that I told you before. And then after they reach the highest point here in this cylinder, then they fall down again and the superposition is recombined and they observe an interference pattern here, say. So they go up, they follow this is in a freely falling frame. So maybe we can look just at this because it doesn't take into account the blue atom. So the atom is split into two different trajectories, then it's recombined, and one measures a relative phase. And this relative phase that they measured is the gravitational action difference. Now, the crucial point of this experiment is that this gravitational action difference is not the gravitational field of the Earth, but it is the gravitational, this is filtered out, the gravitational field of the Earth, but it is the gravitational field of a 1 kilo tungsten mass, that is this half donut here, that is placed at the highest point of the interferometer. So the V that you see here is the gravitational interaction between the atom and this 1 kilo mass. And because of this specific setup that they use, they managed for the first time to measure a gravitational phase shift that is beyond the linear regime. So it's not just MGX, but it's also the higher order corrections. So now what we did with them was to think about everything that we know nowadays from current experiments. What do we know? We know that a localized mass as light as 90 milligrams sources a gravitational field, so definitely the tungsten mass sources a gravitational field. And they measured it also. Then we know that the equivalence principle is valid up to the experimental resolution that we have nowadays, that is pretty good. We know that there are gravitational waves. And then in this experiment, they measured the gravitational phase shift between different paths beyond the linear regime. And also, this is basically a test that classical gravity, that is the one that is sourced by the tungsten mass, and quantum theory, that is the atom in a quantum superposition, are compatible beyond the linear regime. This experiment is perfectly well explained as a quantum particle on a classical gravitational field. So this is clearly not an experiment, proves that the gravitational field is quantum, or that it is in a quantum superposition. But what are we missing? Which principles are we missing, and hence should be tested in order to achieve a superposition of gravitational fields? And we identified 3 fundamental principles, and not all of them are strictly necessary. So I will now focus on 1 and 3, that is enough. And so these are the existence of gravitational fields that states that any massive particle that is well localized at a position x0 sources a gravitational field G with functional form G of x minus x0. So notice that this principle does not say anything about a mass that is in a quantum superposition. So the only thing is that it assumes is that a localized mass sources a gravitational field. And then the quantum relativity principle that states that the laws of physics take the same form in every reference frame, including the reference frames associated to quantum particles, and hence quantum reference frames. So let's take these two principles together and let's look at how we describe these experiments. So this is the lab description from the perspective of a quantum reference frame that is centered on the atom in the interferometer. So now, if we do a quantum reference frame transformation to this particle, then this particle is in a fixed position. But the source particle, the tungsten mass, is in a quantum superposition of two positions. And actually, if you put the numbers, it would lead to, since it's a 25 centimeter separation, it would lead to a distinguishable configuration of the tungsten. And so basically, via a quantum reference frame transformation, we can map this situation where the gravitational field was sourced by an object that is in a classical configuration to another configuration where the source is in a quantum superposition state. So now, this of course doesn't prove that the gravitational field is in a quantum superposition states, because these are these additional assumptions, but this can tell us which way to go, can tell us which other principles should fail if we cannot have a superposition of gravitational fields. Then one of these two principles has to fail, or which principles we should test in order to have a description of physics that is compatible with massive bodies being in a quantum superposition. So this is everything that I wanted to tell you. And just to summarize, I see two reasons why this field is interesting. And the first one is that we do not know which observation would prove in a compelling way that gravity has quantum features. And the second one, that is more theoretical, is that we have the fundamental principles of general relativity and quantum theory, and we do not know how to put them together, and what is the conceptual foundation of a theory that lies at the interface between these two theories. But in this regime, where we have these concrete scenarios, we can test the internal consistency of the theory and have some guidance, find some fundamental principles that will hopefully help us to formulate the theory in the higher energy regime. And then it will be really important to connect with existing quantum gravity approaches. So any idea is really welcome to make progress towards the formulation of a theory that combines quantum theory and general relativity. With this, I would like to thank you for your attention.
Okay, thank you very much, Flaminia, for your very interesting talk.
Thanks.
And very nice presentation of your ideas. Questions, please.
Maybe I can start.
Luca, please ask your question.
Yeah. Thank you very much, Flaminia, for the interesting talk.
Thanks.
So I would like to understand maybe a bit better this notion of quantum reference frame. So if I understood well, for instance, let's suppose we just have two, as we call them, quantum objects that can work as reference frames. Okay, and for instance, in this case, let's just take two, just C and A, without thinking about B for now.
Yeah.
Okay, let's suppose that I'm in C, and I'm a quantum reference frame. I'm a quantum observer in C on the left-hand side, and I'm observing a superposition state, which is this A. Okay, so from my point of view, from my reference frame, I see a superposition in A. Okay, and fine. Okay, now what? Okay, so let me formulate the question. It's a bit. So I am in C and I see a quantum superposition in A. Okay, and you say let's do a quantum reference frame transformation and move the origin of my reference frame from C to A. Okay.
Yes.
Now there will be, okay, from the point of view of A, which was before in superposition, Okay, I'm now in this A. From A, C appears to be in some entangled state.
So if you have only A and B, then A is in a fixed position and C is in a quantum superposition. Once you also add B, so basically.
Okay, so to generate the entanglement, you really need the third one.
Yeah.
So let's just stay maybe with 2. Okay, at the moment. So fine. Okay, so in this case, the notion of superposition is just preserved in the sense that, I mean, I see a superposition from C and A see a superposition from A. Okay, so there is no reference frame in which you kill the superposition, right? It's still
just
there.
that A can be like localized or not according to where you're looking from. Yeah.
Okay. While if you add a third quantum particle, you will also see entanglement, but not from all quantum reference frame. There will be some quantum. Okay.
Yeah.
So there will be some quantum reference frame from which you will see no entanglement.
Yeah.
So in this sense, entanglement.
It really depends on the transformation that, on the quantum reference frame that you pick.
Okay. Now, if we go back to this experiment of Bose, Marlette, Vedral, in that case, it's very important in the end to generate some entanglement, which they say is induced by gravity, right? Now, based on this quantum reference frame relativity of entanglement, let's say, does it mean that there will be some quantum reference frame in which we will not see any generation of entanglement induced by gravity?
So it depends on geometric configuration, but I guess this is possible. Yeah, at least in some configurations, it is possible. Yeah.
But then, I mean, what they say is that if you see this entanglement-induced gravitational, if you see this gravity-induced entanglement, you would have some type of proof of quantization of gravity because you have some superposition of quantum gravitational fields. Okay. But then if there is a frame in which we don't see this entanglement, it looks like that in some frame you would say, okay, I see some.
No, okay, yeah, I understand your confusion. Okay, yeah, no, but okay, so there is an important point that is that this the quantum reference frame transformation changes your notion of locality. So this is why I also do not have a definite answer for what will happen in like for what one can conclude on the nature of gravity, because you're repartitioning your full Hilbert space. So operations that were local initially are no longer local, for instance. And so this means that basically, so incidentally, that probabilities are the same in every quantum reference frame once you fix the state and the observables.
Okay, I see. Then okay,
yeah,
makes more sense. Okay, I see. And maybe, okay, I think this is more clear now. So there will be no ambiguity in that case then.
Yeah,
just
exactly.
to make sure
so,
the findings is good. Okay. And actually, I was not aware of this experiment by the Stanford group because I knew there was this cow experiment where the shift was induced by the gravitational field of the Earth. Okay. But this is amazing. They induced the shift with the gravitational field of 1 kilo, 1 kilo mass. It's crazy. Okay. So it's very interesting. So it's just basically a generalization of the cow experiment to gravitational field of small objects, right? It's more or less the same.
Yeah, it's also much more precise. Okay, there are some caveats, but that's a long story. Maybe, yeah,
okay.
Yeah,
we can discuss another time
with the validity of the equivalence principle, and yeah, so it's a little bit more subtle the difference. Okay. Yeah.
I see. Yeah, because maybe in the case of cow experiment, you can imagine to cancel the gravitational field.
Exactly.
With some,
exactly.
Instead, in the other case, you are in free fall. You have only tidal forces. Okay, I see. So in this last experiment, we really have a proof that gravitational effects induced induce quantum interference.
The point. Yes.
Okay. Fine. Understand. Okay. Thank you.
Okay. Now I see a couple questions. The first question is for Huang Wu. Please ask your question, Wu. Okay.
First, thanks to thanks for your nice talk. Yeah, I want I have one question. In a quantum in a in a quantum in quantum theory, TU the stress tensor change to the operator, and if when we plug in a Einstein equation,
Yeah.
What physics quantity in Einstein equation change to the operator? What quantity change?
So you want to know what happens if in the Einstein's field equation I put a quantum stress energy tensor as an operator.
Yeah.
So in general, yeah.
But Einstein, but this the right hand side is the operator, and left hand side is no operator.
Yeah, exactly. So it's not well defined mathematically.
What physics quantity is changed in left hand side change?
Yeah, so in general it is not known what happens. So the approach that I described, when you linearize it, then you basically get a spin-2 field on a classical background, and then we know how to quantize the spin-2 field. And so you can, in that case, you have a spin-2 field on the left-hand side that is the metric perturbation that is equal to a quantum stress energy tensor, but this is operator equal operator. So in this case, it's fine. In the most general case, we do not know how to do it.
Not do it? Oh.
Yeah, it's an open question.
Okay.
Maybe we can go to the next question. The next question is from Giuseppe Meuccio. Giuseppe, please ask your question.
Hi, first of all, thank you for the very nice talk. And what I would like to ask you is, with respect to the superposition of massive particles, to repeat Feynman's quote, if we trust this superposition to be valid up to microscopic scales, we should have a superposition of space-time of metrics. And therefore, do you also expect to find a sort of equivalent, the equivalent of a Heisenberg uncertainty principle for space-time on microscopic scales, if gravity is quantum in this sense? I mean, a lower bound on the precision on which we can measure distances and times if space-time is quantum.
Yeah, no, so this is well known. So there is this type of bound, and it's actually unsurprisingly the Planck length. and the calculation is not very straightforward, but it would be the analogous of the charge radius for electromagnetism. So, and it's done by looking at the geodesic equation, geodesic deviation, and like estimating the curvature of. So it's, yeah.
Okay, very interesting. Thank you.
Okay, more questions, please. Let's wait a minute. I see one question from Luca. Luca, please ask your question. No. This is a
Shravan.
question from Shravan. Yes, sorry.
Hi, Flaminia. Thanks for the nice talk, and I have a couple of question or comment. I don't know which category it is. So the first thing is, when you mentioned about gravity, the gravity is classical theory. So the main conundrum between gravity and quantum theory is the concept of time. So time is parameter in quantum theory, and in gravity, time plays it. It's a coordinate, and there is a dynamic of nature. So, which I think you did not mention that. So, can you comment about this and how these two different nature of time can be somehow seen in this experimental setup? Maybe that's very too speculative question, but it would be
So,
great.
Yeah, so that's a higher level of difficulty for an experiment to actually look at time, at differences in time. But the idea is to use quantum clocks. So quantum clocks can be very simple systems. So the simplest quantum clock is a two-level system that has two internal energy levels. And you initialize it in a quantum superposition of these two energy levels. And then when you put it in a gravitational field, basically the time it takes to go, like basically the oscillation time between these two energy levels is given by the proper time of the clock. So according to where you put it, then it tells you a different time. So, so I didn't put it in this slide, but there are also measurements now with quantum clocks in the gravitational field of the Earth that resolve the difference in how well these quantum clocks tick. So basically that's the gravitational time dilation at the scale of 1 millimeter. So it's they're really, really precise now.
Okay.
And yeah, and so this is a technology that people are developing, and yeah, again, it's hard to put this type of clock also on top of a mass in a quantum superposition, but conceptually it can be done, and I see no reasons why this shouldn't work. It's just like it's hard. It's very hard to do it.
Okay. And my second question, well, it's more about comment. Basically, when we talk about gravity and quantum mechanics, the most successful thing which we understood, at least in the context of cosmology, in the context of inflation, primordial fluctuations, which are basically quantized fluctuations. So, that are already kind of evidence that we have quantum gravity, not full regime, but at least to linearized extent. So do you agree with this, or you have something to say about this? Because the ultimate question is to see somehow the quantum nature of gravity. So in my opinion, in some sense, we already see it through primordial fluctuations. So, well, in these experiments, maybe this we want to understand how the gravity between the microscopic objects would act. That's what the question we are trying to understand here. So of course it is different, but to witness quantum gravity, maybe we already seen this through primordial fluctuation.
So I'm not an expert in cosmology, so I do not want to make a statement here on a field that I'm not comfortable with. But yeah.
Okay. More questions, please.
Maybe I can ask a short one.
Okay, please.
If no one else, yeah. So this quantum reference transformation, of course, if I understood correctly, is just no relativistic transformation, right? Some quantum Galilean transformation. So do you have any idea what happens if you take some, relativistic version of it? Like
yes,
boost
we have a special relativistic version of the transformation. So we
complete
Lorentz
generalization.
boosts. Yeah, you have Lorentz boosts in the one particle sector. So now the effort where so the direction in which one should look at is to, so far we have considered only single particles as quantum reference frames. And now the next step is to promote quantum reference frames to fields. And this is the, this is the state of the art at the moment. And this has not been done.
Also in that case, you will see some reference frame from which you see entanglement and some boosted reference frame where you don't see entanglement. You get something like this, or? Yeah, I mean, intuitively one would think so, but then when you sit down and do the calculations, I guess that there will be many. I mean, I don't know, because I haven't done it, but for Lorentz boost, you mean, and single particle, or with fields? Yeah, I was thinking just about particles. No, with particles, yeah, it's the same. Yeah, with particles, it works conceptually. It works in the same way. Yeah, with fields, though, since I was just thinking about particles, just particles. Everything. No, with particles, yeah, it works. Yeah.
Okay. More questions?
Because I mean, the notion of quantum reference frame, because if you are sitting on a reference, not sitting, it's not really correct to say sitting, but if you are in a quantum reference frame that is on a superposition, it's a bit uncomfortable to think of it like, I don't know, something from which, but it's very interesting. Okay. There is another question, I think, from Giuseppe Melluccio.
Giuseppe, do you still want to ask your question? Or?
Yes. If I can add something, a question now that you have talked about second quantizing quantum reference frame. I was thinking about if you do this on curved spacetime, where we know that the vacuum state is not uniquely defined, then for example, Bogulabov coefficients could be interpreted as a sort of quantum reference frame change, right?
Yeah.
And so of course also the number of particles in some sense would.
Yeah, exactly, and that's why you need in that case a field description, because the number of particles. I mean, you can have particles like disappearing or appearing, and
that's because that's
have no reference frame
energy. Because that's related to energy, of course, and so the notion of conservation of energy.
Yeah, exactly. Yeah.
Hard to grasp.
Yeah.
I see.
Okay. More questions? I don't see more questions. So let's thank Flaminia once again for her very interesting talk.
Thank you very much.
Thank you very much for your talk. And don't forget to send your presentation. Don't forget. Thank you very much. Bye-bye. Our seminar is closed. Yes. Bye-bye.
Bye-bye.
Thank you.
Thank you very much.
Bye. Thanks.
Alexei, maybe we can speak about the grant tomorrow. Okay? Evening.
Yes.
I can speak something about